Hello and welcome to Naturally Curious. This is a show where I pick the brain of different cool people every episode. I'm Clayton Law, and today I have the absolute pleasure of being joined by math professor Stefan Bilaniuk. Let's go way back, and I noticed in your lecture you have said that you weren't good at math when you were a kid.
That's very true.
So it was not natural to you then, it was difficult?
Well, in elementary school, I had a lot of trouble with arithmetic in particular. And around grade 2, I actually told my parents I was so frustrated that I had to give up taking math anymore. And my parents, much to my disgust, informed me that that was not an option in grade 2 and that I would have to take it for several more years.
So what changed from hating math to now being a math professor?
Okay, so somewhere I got to be good enough at handling things when algebra started happening that I started doing somewhat well in high school. And then in the last year of high school, it really kind of all started clicking together when I was taking calculus, of all things. And I started thinking it might actually be cool. And I needed to take a lot of math because I was interested in doing science. So what happened in the end was that in first year, I took philosophy and computer science and mathematics and physics courses, because all of these areas actually looked at the problem of the question of limits to knowledge from different points of view. And that was what I was really interested in and still am. And unfortunately, most of them ruled themselves out. Philosophy, they had been going on the same problems for 2,500 years. Computer science was extremely frustrating because it was part of the last group at the University of Toronto to be using punched cards, right, to do programming in first year. And they weren't maintaining the equipment anymore. And I wasn't learning anything new because I had taught myself all of that stuff on my own in high school anyway. Physics was very frustrating because unfortunately the lab equipment was more sensitive, which meant it was more fragile, which means I looked at it and it broke. I wasn't good in a lab. And then the math courses were actually brutal. I took the highest stream of math courses that U of T had at the time. And my college advisor had said, that with marks in only the mid-90s in high school, right, in the maths, that I should probably consider taking the next lower stream down. And of course, I was cocky and didn't listen and took them anyway. And let's just say that my first test, I got 14% on before the marks were raised, 15% all around because of a problem not having a solution because of a typo. Basically, after the first 6 weeks or so, it became apparent that I was in way over my head. And I didn't dig myself out of this before the end of the first term. So I was incredibly lucky that both algebra and calculus were actually full year courses. Because after the Christmas exam season was done, I had a cumulative 51% in algebra and 37% in calculus. Basically what happened was I turned into a mathematician to get out of first year alive because I was too proud to drop the courses because my then girlfriend, who read the writing on the wall, actually did drop them and dropped to the next lower level down. She wanted to do computer science. That was all she needed. And she was smarter than I was. So
you really weren't interested in math until you said grade 12 high
somewhere
school.
On grade 13, actually.
Grade 13.
I'm one of the old ones. So,
but if you didn't like math back then, what did you like? I'm saying between grade 1 to grade 11, that kind of, did you want to be like a baseball player?
No, I actually wanted to be a scientist. I wanted probably to be a physicist because I had a granduncle who was a physicist, and I didn't want to do anything like what my parents did, which was, they had doctorates in the humanities, in theology and history for my father and in German literature for my mother. And I really didn't want to be doing the same kind of thing just because it was too similar. Okay.
By what time did you know that you kind of want to become a math professor?
Oh, okay. So I came to the conclusion that I probably wanted to go on in math after first year, right? Because I ended up succeeding in those courses, although, I mean, after that near disaster, I ended up getting, like decent marks at the end. I had an A- in calculus and a B in, no, it was an A- in algebra and a B in calculus. And after that, I managed to dig myself, like I had a really good second year, right? Where I had marks that were all A's or, in A territory one way or another. And consequently, I felt I really could go on in this, and I did, right? What was really interesting to me in retrospect was that it wasn't until I was actually doing research in graduate school and at the same time, like working as a teaching assistant, that I came to the conclusion that I actually like teaching it more than I like doing research in it.
Well, how long have you been teaching for now?
Well, let's see. I've been at Trent for 27 years.
Oh.
I did some teaching each of the 2 years before that while I was postdocing. And then I actually had lectured was a lecturer in 4 different courses while still a graduate student at Dartmouth College. So if you go back all the way, that's about 32 years now, plus another 3 years as a teaching assistant.
Let's say 35 then.
So call it 35, sure.
You've been teaching for 35 years, and you've obviously been like academia environment for longer than 35 years then.
Yeah.
Do you get bored?
Now and again I do, right? But the things that are actually really boring are getting stuck on, like trying to do problems that I find interesting, but which are harder than I am. And which is unfortunately what happens with most of my research career.
We'll keep that in mind because I have some questions about that later.
And on the other hand, one of the problems with being an academic is the same as being any kind of teacher. You have a lot of donkey work to do, okay? And parts of that are not enjoyable. Dealing with administration is often not a great thing because there's paperwork and it's kind of pointless sometimes. And the other thing, the real bane of everyone's life is marking. Okay. I haven't met a whole lot of people who actually enjoy marking past the first couple of times they actually have to mark something.
You have published 2 textbooks, am I right? One on mathematical logic and another one on projective planes.
Yeah, I haven't in a sense published them other than sort of, releasing them on the internet, right, with a free license, but yeah.
How long did it take you to do each one of them?
Well, the first cut at the mathematical logic textbook took several months to write. I did that during a sabbatical early in my career, I think 94, 95, something like that, or 95, 96, somewhere in there, mid-90s. And I have since put out various improvements to it, but the last one was now about 15 years ago. So I guess overall that one took several years.
Mm-hmm.
Okay. The other one, I think from start to finish took several months again to do the first cut, but I only did another year's worth of improvements or so before, like leaving it alone. It turns out that I haven't been using it very much, so I haven't had much incentive to improve it.
Well, why did you write them in the first place? Because you said you'll enjoy teaching. Writing textbooks, I imagine it would be very different from teaching, actually.
Well, I was teaching a mathematical logic course here at Trent that I had developed right when I arrived, but there weren't any textbooks that I really liked for that, and so I decided, to basically write my own, right?
Okay.
And something similar happened for the projective planes book, because we also have a course on projective planes and non-Euclidean geometry, and for the projective planes part, there wasn't anything that was compact to use.
So you didn't write the textbook because you want to write them. Like, it's not because you enjoy writing textbook.
I don't enjoy writing. It's something that I have to do right from time to time. The rare cases where I enjoy it are where I get to, write some little comic poem or something, right, or something that has an extended in joke, right? Like, things like that I occasionally enjoy, but they're really short little things that fit on a page, right? Typically, right? And very rarely more. So,
Well, speaking of that, you're gonna write any more of those? Like your opinion piece, is mathematics a science?
I haven't written anything more quite like that, but I have written some modest little poems, including the sort of take on the lores, the I guess lore that Gandalf relates to Pippin on the ride to Gondor, where he goes over the rhymes of lore of how the Númenóreans arrived, right, and the Seven Stones and all that stuff. And I wrote one that takes off on this and does a finite projective plane called the Fano configuration.
Okay.
I had a lot of fun doing that.
Okay.
Stuff like that.
Between 1996 and 1999, you hoisted things in SC137.
Yes.
Why? It doesn't seem very useful. It doesn't seem very is it just for fun?
It was basically for fun. It did serve a sort of useful purpose in giving the students something to be amused about, which tended to diffuse the tension in calculus classes, right? Which is a useful thing to do because a lot of people are anxious. It also gave me something to do when they were writing quizzes or tests, because I would build little mobiles out of cardboard cubes and string and things like that. And I did once, when I actually had an exam in that room, build a really huge mobile, right, which I saved up a lot of, things for several weeks beforehand. But this kind of thing gave the students the idea that, the things should be hoisted, which was kind of ridiculous, but oh well.
Can you still do it nowadays?
You can. The cable and the hoisting arrangements are all still in that room, and I do occasionally use it to hoist my book bag right up or something like that.
I know, like, professors and teachers are supposed to say, "Oh, there are no dumb questions. There are no stupid questions." But what is the dumbest questions you have ever received in class before?
That's hard to decide. I mean, there are these. Probably the dumbest ones are the ones where somebody is having a brain fart and they're not seeing what's precisely in front of them on the board, and they ask, like, how did this thing at the end of the board happen, right? And all you have to do is back up a step, or two on the board to see how that went down. And in many cases, what happened where it was that people were scribbling away, and then they sort of looked at the beginning and they looked at the end, and they sort of failed to look in the middle, right? Okay. That kind of thing. But that's not really a stupid question so much as it is, I guess brain sensory, fart. Yeah, brain farts.
I imagine, like, there's no dumb question like what's -1 minus -1.
Okay, so that kind of thing would be extremely rare, say, in first year calculus. What is rather more common are people botching algebra. Okay, so the next time somebody takes something that looks like 1 over a plus b and takes it apart as 1 over a plus 1 over b, I'm going to be tempted to dump their body in the river. Okay. But for the one that you mentioned in particular, right? Minus times minus makes plus. The reasons why we don't discuss, right? Okay.
Yeah, actually, speaking of things that we don't discuss, why can't we divide by 0?
Basically, because there's no reasonable way for that to make sense. Okay, 0 got invented sometime in early medieval India, right? I mean, the earliest mentions I think we have are in Aryabhata's writings. But they didn't really sort of start getting serious about working out the algebraic rules, as far as we can tell, until a century and some later, when Brahmagupta actually tried to make sense out of things like dividing by 0, and didn't really succeed, right?
So when you say divide by 0 will be undefined,
yeah, basically. Is it
really just undefined in the lower level of math?
No, it really is undefined.
So it really is undefined, yeah. Even for...
Yeah, you can often make sense of things, like as this expression, in the denominator approaches zero, that the fraction goes to infinity or something like that. But that's really as close as you can get. Okay, I mean, if you're talking about the actual genuine zero, right, the one that absorbs everything when you multiply, dividing by it simply doesn't make any sense. Okay.
Let's talk about coffee. It seems like every single time you go into a lecture, you're holding a cup of coffee.
No, sometimes I hold a can of pop with caffeine in it.
How do you like your coffee?
I like my coffee black.
Okay, well that's very mathematician of you.
Well, the late Paul Erdős, who was a great mathematician, commented that a mathematician was a machine for converting caffeine into theorems. And he had a point.
You often make fun of physicists, engineers, and computer scientists. That kind of reminds me of how the Army makes fun of the Navy makes fun of Air Force. Is it just like that? Just plain fun?
Yeah, it is fun. I mean, look, my family is lousy with, other than teachers and things like that, it's lousy with engineers. 2 of my 3 brothers are engineers, right? I have several cousins who are engineers. My granduncle, the physicist, started out as an engineer, and so on. What I mean by it's lousy with engineers is that there are lots of them. Right?
Oh, okay.
Okay.
Do you have a favorite number?
41.
Why?
Because it's the 13th prime number. And if you want to scare the people who are afraid of the number 13, and you want to do it in a way that they don't notice until you tell them, 41 is the way to do it.
Speaking of prime number, what is the point of keep looking for a bigger and bigger prime number?
Part of the point is to actually exercise computer hardware, and part of the point is to find lots of big primes so that you can try to spot, like the interesting patterns that primes may have that we don't know how to prove. Like, are there infinitely many twin primes where they differ by 2? Like 41 and 43. Okay. And the fact is we don't know, and we don't know how to prove it one way or the other. Okay. So far, eventually we seem to keep finding bigger and bigger ones, but does that go on forever? We don't know.
So there are lots of works in math that based on the assumption that the Riemann hypothesis is true. What will happen if it's not?
Well, if it's not, then people are going to have to go revisit that, right? All that stuff. Some of it in fact has been shown to work, in other ways, right? Some of it may end up, having to be redone from scratch. Some of it may turn out to simply be wrong if the Riemann hypothesis is actually wrong. Okay, it's really hard to predict for each individual thing.
It's just kind of interesting to see their work that based on assuming the fact that something that has been unproven to be true.
Well, yeah, but that comes of things being a little bit frustrating, right? The Riemann hypothesis is something that most people believe to be true. And on the other hand, it's also something that is obviously extremely difficult to prove, at least so far it seems that way. Consequently, if you want to sort of look beyond it, your choices are go back and prove the Riemann hypothesis. Well, I don't know how to do that. Or use it, right? And hope like hell that someone else can manage to make it work, right? So,
do you have a favorite mathematician?
Oh, that's a hard one. That's a really hard one. I guess I have a small group that I consider favorites, but probably my top 2 would be respectively Archimedes and Kurt Gödel.
I've never even heard of the second guy.
Okay, the second guy was a mathematical logician in the last century. He died in the 70s, I believe. He's the guy who proved the incompleteness theorem for mathematical logic, which basically says that if you have, like a reasonable machine checkable set of axioms and rules of procedure, and the system's powerful enough to do basic arithmetic, then it's not powerful enough to prove it has no contradictions in itself. Okay. And that is a real limitation on what you can actually do by way of trying to prove that mathematics is actually internally consistent.
Okay. So there's a thing that I want to make as a recurring thing in the show. The idea is like how a lot of people have heard of big names like Gauss, like Newton, like Archimedes. But yet not a lot of people know exactly what they have done. Just like how when people say, oh, famous philosophers, oh, Plato, Socrates, what have they done? Oh, Plato did the cave thing. That's about the only thing I know about. And I'm like that when it comes to like other things that I'm not as familiar with. So I'm just going to say a few names, and can you quickly just briefly talk about what they have done in their lifetime?
Well, insofar as I know that, right, keep in mind that, I don't know everything. So
Yes. I think a lot of people know what did Newton do, so let's skip Newton.
Okay. Although he did a lot more than most people are aware of. So.
Oh, of course. I mean, what did Gauss do?
Okay, what didn't Gauss do? The problem with Gauss is that he did just about everything, but he didn't publish. Okay, so Gauss invented techniques for doing computations of orbits, and out of that fell a good chunk of modern statistics, because that's where he found the normal distribution by looking at errors in astronomical observations. He did
normal distribution is the bell curve.
Yeah, the bell curve. Yeah, he did massive amounts of work in various parts of algebra. He's the guy who did an initial proof, although it turned out to be slightly wrong, and then he did several more proofs in his life to make up for that. Over the complex numbers, every polynomial can be factored into linear factors. Okay, and that was like a massive advance in algebra. It's now called the fundamental theorem of algebra just because of that, although it's something that most people aren't aware of. Okay. He did massive amounts of work in number theory. He did, modern number theory basically goes back to one of his books, Disquisitiones Arithmetica, if memory serves me. He did all kinds of work in geometry and non-Euclidean geometry in particular, which he didn't publish and didn't even mention to other people until other people had published, right, and so on,
People have said that if somebody asks you who came up with this math thing, you answer either Gauss or Euler, and you're probably right 9 out of 10 times.
Well, you're very likely to have that one of them worked on it, though whether they were, like the key persons in whatever happened in that area is another matter. Okay.
And I've also heard that Gauss was the last person who knew everything about math of their time.
It's a pretty good bet that he's probably the last person who could have said that he knew everything that was important, right, in the field, but even he probably couldn't have claimed to know every little detail.
People know Euler because of Euler's identity, e to the pi I plus 1 equals 0. Can you explain that a little bit?
Well, okay, there are several different ways you can get at it, but basically if you plug, instead of plugging x into the infinite series for e to the x, you plug in I times x, what you get is the series for cos plus I times the series for sine. Right, so you have a relationship via the complex numbers between two of the basic trig functions and the basic exponential function. And once you have that formula and you plug in pi in for x, right, cos of pi is 1, sine of pi is 0, right? So, cos of pi is -1, my mistake. So e to the I pi is equal to, right, cos of pi, which is -1. And there you are, right? Okay.
It's kind of it's the what they call it, the most elegant formula.
It's one of the very elegant ones. It actually was known before Euler. I think de Moivre already had that formula.
So Euler's identity was not discovered by Euler.
Well, there are a lot of things named after people that weren't discovered by them, but they're the ones who sort of made it popular. One of the reasons why a lot of Euler's notation and terminology and equations like that have become associated with him was because he was one of the very few truly high-powered mathematicians who also wrote textbooks intended for ordinary mortals. Okay. And he wrote pretty good ones, even if they're occasionally a little bit sloppy in how they do things. So,
what are you working on?
What am I working on? At the moment, I'm not working on very much. I have in the back of my head that I occasionally come back to a problem in set theory and a problem in projective geometry, respectively. But they're both things that I have been cracking my head on, I suppose, because I only have the one, for a couple of decades, right? With at best marginal progress. So, but while I'm having a really busy teaching term, I only occasionally get to come back to them. So at best, right?
I have questions about doing math in higher dimensions. It's already hard for somebody to imagine 3 dimensions because we write stuff on a piece of paper, and a piece of paper is 2-dimensional.
Yeah, really thinking in 3 dimensions is harder than it looks, right?
Is it even possible? Is it even physically possible for someone to imagine 4-dimensional space?
Well, I think what you're really asking is whether it's mentally possible. And the short answer is yes, but with enormous amounts of effort. The reason why people, invoke abstraction in mathematics so much is so that they don't have to put in the kind of effort that's needed to do that kind of visualization. Now, in the 19th century, there was an Anglo-American, he emigrated from England to the States, mathematician named Peirce, who developed techniques for training yourself to visualize things in 4 and 5 dimensions. And then he taught them to his kids, which I think was probably cruel and unusual. Okay. I'm not sure. I don't know how the kids reacted to this, but I probably wasn't terribly well, would be my guess. On the other hand, people who work a lot in that kind of in 4-dimensional and 5-dimensional kind of space, and somebody, for example, who works in general relativity a lot, would be used to doing that, would likely develop a certain degree of intuition even without going through a training regime like that, right? So they would effectively be able to visualize it. A lot of people who work in areas like that nowadays rely a lot on computers, right, generating projections that are useful to them, right, of this kind of stuff. So for example, the people who look at minimal surfaces, right, do a lot of what amount to experimental work by, throw up some kind of wireframe on the computer and then have a computer work out, some soap bubble, right, that interconnects, right, the different parts of the frame. And people have found entirely new classes of minimal surfaces that way. But that's a really, really different kettle of fish, right, from actually being able to, fully visualize what you need to do that, because that's an optimization problem that if you truly visualized it would actually be happening in higher dimensions, right? Because you're graphing something that has 3 dimensions of input in a higher dimension and then taking a look at that, right? So.
Do you get asked for help from physics students?
I do that. I do get that every so often. The most common example, actually, in recent years has been with students who are interested in learning the math behind general relativity. I've been on a actually fairly regular basis the last 3-4 years. I've been offering a course as a reading course on calculus and manifolds, which is basically doing calculus in higher dimensions on surfaces which have curvature. Right? Okay. Which is what you need for general relativity in the low-dimensional cases. Okay, and the problem is that the physics department really doesn't have anybody who does general relativity at the moment. Okay, and consequently, it's hard to for them to go and learn that material on their own. So they need to take a course on that. Okay.
When was algebra invented?
That depends on what you mean by algebra. If you mean by algebra, like being able to solve problems that we solve by algebra, then we have to go back to ancient Egypt and ancient Mesopotamia, right? Where people 4,000 years ago, knew how to solve various problems, like x plus x over 7, right, is equal to 30. They would be able to solve that kind of thing for x to whatever approximation you wanted. I mean, there are problems very similar to that on ancient papyri and ancient cuneiform tablets. On the other hand, if you're talking about like algebra done with symbolic notation and manipulated using that symbolic notation, probably the beginning would have to be the algebraic shorthand that got invented by Diophantus, who was a mathematician in Alexandria who lived about 250 AD, give or take about a century. Okay, we know very little about him. And in his Arithmetica, which is mostly about solving equations in integers and rational numbers, he actually had developed a notation to express simple kinds of equations, so up to, like cubic equations in one variable, using a kind of shorthand notation. And that's the first real cut. It's something like algebra in a form we would recognize.
So before that, people didn't use variable like x and y.
No, yeah. So they would throw around, right, words like unknown, right, or desired quantity or something like that, right?
So it must be very hard for ancient Greek to prove something because everything is much longer, much harder to write it out.
Okay, well, most of the context in which proof got introduced into mathematics was in geometry rather than in anything that had algebra or numbers attached. Okay. And it took a little while before numbers started getting attached to that, in fact. So, for example, we tend to think of a right angle, right, as being, 90 degrees. So we have a number attached to that. But to an ancient Greek geometer, especially near the beginning, a number would not have been attached to that because right angle was when two lines met perpendicularly. So it was half of a straight angle, if you want to think of it that way, right? There's no number there, okay?
Are there any proofs or theorems from that period of time that would have looked different back then?
Well, the obvious example would be the Pythagorean theorem. I mean, we tend to think of that, okay, you've got a triangle with sides of length A, B, C, right? If it's a right triangle and the right angle is between the sides of length B and C, then what that's telling you, right, is that A squared is equal to B squared plus C squared. Okay, the way an ancient Greek would have thought of that, and if you actually look at the diagrams in Euclid, I think it's proposition 46 or 47, somewhere in there, in book 1. The way they would have thought of that is you actually have a right triangle, and on each side you attach a square, right, which has sides of that length. So you have this kind of petal formation, right, of three squares around a triangle. And then what you actually do is you do some kind of argument to show that the two smaller squares have a combined area that's equal to the larger square. Euclid's is particularly less than transparent. There are much better arguments that other people invented. So
I was watching a video about how we should communicate with aliens if they were to contact us. Well, obviously English won't work, any language won't work, but math is universal, so we can say 2 plus 2 is 4 in a way where everyone can understand, like putting 2 dots and 2 dots together makes 4 dots. Mm-hmm. And people suggest using the Pythagorean theorem because it is an advanced concept, yet extremely easy to show because of what you just said.
Yeah.
Can you give me another theorem that is easy to show, yet quite advanced?
I would probably cite one of what is very likely the earliest result that had a proof, although we don't know what the original proof was anymore, and that's Thales' theorem, right? Which is that if you take a circle and you draw a diameter, and you pick any other point, right, somewhere on the circumference of the circle, and you connect it to the two ends of the diameter, that you make a right angle.
Oh. When was this proof?
So this result, according to later commentators, was proved by Thales of Miletus probably around 600 BC.
So this can be another theorem we can use to communicate with aliens. Stefan, thank you very much for joining me for this episode. It's been a pleasure having you.
Yeah, and it's been fun doing this. I look forward to listening to myself.
Until the next discovery of the largest prime number, stay curious. This is me when editing for this very first episode. Thank you everyone for sitting through all the mistakes I made during the interview and all the mistakes I made in editing. I promise come back next week for episode 2, and it will be much, much better. Thank you.